So Benjamin both received the diploma engineering degree in electrical engineering from the Aachen University in Germany in 2008. In 2009, he joined the Fraunhofer Institute for Telecommunication in Berlin, Germany, where he is currently heading the video coding system group at the Video Communication and Application Department. And in 2011, he became a part-time lecturer at the Aachen University of Applied Science in Berlin, HTW University of Applied Science Berlin. Since 2010, Benjamin has been very active involved in the ITUT Video Coding Expert Group and the ISO IEC Motion Picture Expert Group Video Coding Standardization Process as a technical contributor, coordinator of core experiments, and chief editor of the High Efficiency Video Coding Standard and the new Versatile Video Coding Standard. The title of this talk will be the new Versatile Video Coding Standard, Open Implementation and Application. So Benjamin, you have the floor for 30 minutes presentation.
Yeah. Thank you, Wasim, for the kind introduction. And I'm feeling honored to be invited to give this little talk today. And hello and welcome everyone to my talk about the open implementations for VVC and their applications. Let's start with a short outline for today's talk. Starts with an introduction, then I dive more into the VVenC and VVdeC open source VVC implementations that we released at Fraunhofer HHI, and at the end I will give an overview and explain a bit about the applications for these two encoder and decoder implementations. So with an introduction, let's start with zero. So the video coding challenge, maybe just I always like it to remember what we do in video coding and how challenging the task is. So consider an HD video. That if you have a YUV 420 format, where's the pointer, laser pointer here. So uncoded, you have HD 1080p video, 50 frames per second, 8-bit. So just standard SDR HD, full HD video is 1.24 gigabits per second. Then we encode that with a modern encoder. We get a very good quality at 5 megabits, and this is 0.4% of the overall size. So this is where this is the efficiency. I think we need to always think about that in which context we are working here. So just a very tiny fraction of the original size what today's video codec achieve, and at the decoder size, this is going to be decoded again to the full size. But just keep that in mind, that tiny fraction that we achieve to encode a video into a bit stream. So a short history of international video coding standards. I will keep that short. So we had MPEG-2, AVC, H.264, HEVC, H.265. Every new generation gives approximately 50% reduction, and so AVC is prominent, HEVC is getting more and more traction. So do we need more efficient video coding is the question that is always asked. But there's from the Industrial Revolution, there's the Jevons paradox at that time with coal. So if you make a resource the consumption of a resource more efficient, so the consumption tends to increase rather to decrease, because if you make a steam machine more efficient, so it consumes less coal, more the usage of steam machine increases, so the overall consumption of coal is increasing. So this is the same effect in video. If you make video very efficient, a lot of stuff gets used in video. I will show some more examples. For example, here in gaming. So streaming of gaming is a big thing, and also in some markets already the majority of bits transmitted. You have social media. You don't send pictures anymore. In that case, Jack Black sends out little TikTok videos. So this is something that is new. It's not just TV, it's just gaming, social media, and of course, what we do here, and I guess a lot of you guys are doing that every day, is teleconferencing. So screen sharing, video conferencing, and that. So it's much more than TV. And also, if you look at the latest Cisco annual internet report, this one predicts for the future, just looking at one sector that is currently growing, is the connected home. And for the connected home, they looked at the bandwidth for different type of applications. And here it starts with 16% UHD cameras, UHD streaming, 60 megabits per second. But then it goes up to UHD virtual reality, HD virtual reality, 8K TV. This goes to really huge bandwidths. So the expectation of the Cisco report is that also the required bandwidth for future applications in the context, for example, of connected home is increasing as well. So at least after looking into that, I would answer that question, do we need more efficient video coding, as yes. So here we target again 50% with VVC. This is just a rough number. I will get to that on the next slide, on the next slide. So VVC is targeting that yet another step of bitrate reduction. It was finalized in July 2020, so 2.5 years ago, with the goal of 50% bitrate reduction over the predecessor, which is the H.265 HEVC standard. And special focus, you can already guess that from its name, is versatility. So it targets video beyond standard and high definition. So beyond this full HD SDR video that I've pointed out at the beginning. So 8K UHD with HDR, wide color gamut. So really vivid pictures, increased fidelity in video pictures. Adaptive streaming with resolution changes. So we have more and more adaptive streaming usage, and there you can seamlessly switch resolutions. Computer generated screen captured content. This is the type of gaming that I was mentioned. Also screen sharing. My slide presentation here is a typical representation of this type of content. Gaming is a very rising application. Immersive video, VR, AR, and we've seen there that the rates there are projected to be super high, so high compression there is needed. Yeah, so here we are with VVC. Oh, I can see from. And let's look at the efficiency of the reference software model for VVC that was used during the standardization and development of the VVC standard. And here we compare it to the HEVC, so the predecessor reference software, HM. So the encoder control of both reference softwares is pretty comparable. So when you see here the latest version in this chart 11 provides for the same PSNR, so objective quality metric, 41% reduction. It started, you can see here, an interesting point is at the beginning. The first version during the development started at 11%, and then we developed more and more tools and algorithms until we reached at the end 41%. And if you compare that to the reference software gains in times of HEVC, that's higher than what we had during HEVC. However, this is PSNR, objective error metrics. What counts at the end is subjective quality. So what is the bitrate reduction for the same subjective quality measured by means of mean opinion score, or MOS? And in order to do that, we did verification tests. So we did formal lab tests with naive viewers for different applications and usage scenarios. before I dive into the results of the formal subjective testing, just a short note on the runtime, rough measurement of complexity. At the end, the encoder of the VVC reference software was 7.4 times slower than the encoder of the HEVC reference software. So this is a good rough estimate of the complexity, while the decoder was only, this is the black line here, 1.6 times slower. So this is what we kept in as a principle in the past, to have allow more complexity increase on the encoder, where you have some flexibility, but the decoder that needs to be implemented on all devices, supporting all the tools, you try to keep the complexity low. So now back to the subjective test results in the so-called verification tests. Here's an overview where you can see PSNR in orange, bitrate savings for same PSNR in orange, and the bitrate savings for the same mean opinion score, so subjectively tested perceived quality, in green, 4 different scenarios. So the first test was focusing on most common use case is UHD SDR video. You can find that in the in this document, JVET T2020. And here you can see that PSNR on the tested sequences. I have to say that the tested sequences are different sequences than the ones we use to develop the standard. So you do not optimize it on the test set. So a completely different test set was used in the verification test sets that has not been used during the development. And here you can see that the PSNR-based savings is even less than 40%, while the MOS-based savings are over 40%, so 42, 43% savings for SDR UHD. Then we had HDR video. And here you can see that really the improved efficiency for these use cases in VVC, they kick in. So you have almost a bit less and a bit more than 50% savings compared to HEVC for hybrid log gamma HDR content and perceptual quantizer, PQ HDR content for the UHD resolution both. Then there was an SDR HD test, 360-degree video, immersive video test, low delay conversational streaming application, gaming, screen content type of scenarios. And all these scenarios, you can achieve over 50% for some 360-degree scenarios, and between 35 and 40% for these conversational scenarios. So the 50% is the label, but it really depends on resolutions and applications. So that's why I tried to collect here all the data that we gathered during our verification tests. So the high subjective gains of VVC are generally confirmed by these verification tests with 43 to 50% for the reference software. We also throw in our open VVenC encoder, which is an open source implementation, which I will talk about on the next slides. And there we achieved an even higher gain due to some tuning and tweaking and optimization, which you would do in a real world encoder. So you still can achieve more when tuning your encoder, but the same, of course, applies to HEVC. So, the reference software comparison, I would say, is fair, but we throw in an optimized open encoder to see what you can get more. And this is then about 50% in these tests. Yeah, that brings us to the second part about aforementioned VVenC, and there's to the VVenC encoder, there's also an open source decoder called VVdeC, and these are the open and optimized VVC implementations I want to talk about on the next slides. They are available on GitHub since September 2020, so July was when VVC was finalized, August, September. So 2 months after finalization of the standard, there was the very first version of VVenC and VVdeC made available on our GitHub repository. You can see on the picture here. The versatile video encoder is a software encoder, or I will call it VVenC from now on, is so far the most efficient and fast open source VVC encoder and even open video encoder. VVC is the most advanced standard. So for all the open available implementations, VVenC is for the fast offline encoding use case the most efficient one. And exactly it targets fast offline encoding with random access. So if you want to do a conversational, low delay, live encoding, this is definitely not the software where VVenC is not developed for this use case. But if you want to do fast offline encoding, for example, in a cloud or on your workstation for random access, let's say video on demand use case, then this is the right application for VVenC. And I will talk about applications towards the end of the talk. Then the decoder is open source software decoder. It's the fastest fully compliant open source VVC decoder at the moment, and it targets UHD 10-bit live decoding on an powerful x86 computer or one of the more recent Apple ARM devices. They can also achieve UHD 10-bit live decoding on these machines. And on a mobile platform like a phone or a tablet, you can do HD live decoding. How this is going to be then used in applications for smartphones, I will come to that also later in this talk. VVenC, so let's start with the encoder. If you consider the chain, start at the beginning for the encoding. The main features of the current version 1.7 of VVenC are 5 predefined quality speed presets from faster to slower, while the fastest presets have a lower efficiency and the slower presets have increasing coding efficiency. The more time you give the encoder, the more efficient it can be. So depending on your application and use case, you can choose a preset that suits your need. And from faster to slower, you can have, or that should be actually the other way around, 2100 times speed up for faster over VTM using 8 threads, while VTM is single threaded for UHD content. And for the slowest preset, where you have exactly the same coding efficiency as VTM, you're still 21 times faster than VTM if you use 8 threads, I have to say. That it has real-world features that are typically missing in the reference software. So reference software is not only slow, but also just focused on the compression algorithms and not like non-normative real-world application features like multi-threading, 2-pass, 1-pass and 2-pass VBR rate control, subject quality optimization. I already mentioned that in the verification test. VVenC, although much faster than the reference software, performed visually better than the reference software. And this is exactly due to that subjective quality optimization. It has a simple, easy to use C interface, so it can be integrated in other applications. This is also something related to the application slides towards the end of this talk. It supports arbitrary interperiods, so you do not have, like in the reference software, you have a group of pictures that is fixed with 32 pictures, and then you can only have an iframe at the end of these 32 pictures, so that your frame period has to be a multiple of these. And in a real world encoder, you would just want to define in which interval, you won't have your iframe. So this is also possible with VVenC. And of course, we are happy to see first non-HHI contribution. So we started that, we provided the initial versions, we still work on that and continue to improve that, but we also appreciate non-HHI contributions. So at some point, we would like that people really start using that for their applications and contribute also to that. So we did the basis and the start, and I hope at some point more and more external contributions will come up. So in terms of efficiency, so what is the efficiency of VVenC? You can see here the relative encoding time, and as well on the x-axis pointer here, and the bitrate reduction in percentage relative to the HEVC reference software. So your point here, 100% encoding time is the HEVC reference software, and 0% bitrate savings is also this point here. So this is the reference, or the anchor is the HEVC reference software, HM, the newest one, 17. And in relation to that, you can see that at 42% PSNR-based bitrate savings, is the VTM, the VVC reference software in its newest version, but it also has about 700%, so 7 times the encoder runtime than HM. So this is more or less aligned with the numbers I've previously shown with HM16 and VTM11. So this factor is about the same. Then we look at the first version of VVenC that was released 2 months after VVC was finalized. This is version 0.1, single-threaded, the gray curve. At that time, we only had 4 presets. So slow, medium, fast, and faster. And you can see that the slowest preset was about the same speed as single-threaded as the HM, a little bit faster than HM, and does not have the full bitrate savings of VVC. So now version 1.7 from December last year, so 3 months old. Single-threaded has the green curve here. So we managed to get VVC reference software VTM efficiency again here at the slowest preset. Still much faster single-threaded than VTM, and only a factor of 2 slower than the HM software. But if you enable multi-threading with 8 threads, we are about 30% of the HM reference software, so even much faster than the HM reference software. But then if you go to the faster preset, you're just a fraction. This is really fast, then just a fraction of the HM reference software runtime, but still having almost 50% savings compared to full-fledged HEVC. So overall, these years that we released, since we released the first versions, the single-threaded version got 6 times faster than its previous version, and multi-threaded with using more threads, 8 in this case, you get 32 times faster than the first version of the VVenC encoder. And efficiency-wise, we managed to add 8% of coding efficiency gains to the slowest preset. So this is a very nice development. We are about to release a new version 1.8 in April, which is again about 10% faster for the faster presets here. So the curve is again flattening. So this is exactly what we want to achieve here. It's worth then looking at where we are. This was all compared to the HEVC reference software. Here again, the HEVC reference software is 100% runtime, 0% bitrate savings. And then we compare what typically other open available encoder perform in terms of PSNR-based bitrate savings for HD and UHD. All codecs are optimized for PSNR, so exactly what we measure here. And we measured the slower presets of X265. According to my knowledge, the most recent version, 3.5. And you have the slower, very slow, and placebo. They are much faster presets, so X265 gets faster, but also the efficiency then decreases steeply when you go faster. So the fastest presets for VVenC is a bit faster than the slow preset from H265. So if you have experience with X265 and you know, well, slow performs with that speed on my system, you can expect a VVenC in its faster setting a bit faster than that, but a huge increase in coding efficiency. So for the same speed as the slower presets in X265, you get an enormous bump in coding efficiency if you would use VVenC and of course the VVC standard compared to HEVC and the X265 implementation. Here again, both are multi-threaded with 8 threads. So then we have PSNR, and then we used a more subjective tuned metric, MSSSIM, and tuned the both codecs X265 and VVenC for this metric, SSIM. And here we get the same behavior. The fastest preset is a bit faster than slow, but you still have more than 50% bitrate savings over that. So in this open source encoder implementation, you also get your 50% promise. So that's, I guess, good to see that that also holds true for these implementations. So what are the fast and efficient algorithms for VVenC? One key aspect of VVenC are these presets. So from faster to slower. And we developed these presets using an iterative Pareto set optimization. So we started with a very stripped down config, which you can consider HEVC-like, all the tools off, just quadri partitioning, and then did tool on tests on top of that, and then sorted the tools that has the highest coding efficiency for the moderate runtime. So you can have a slope. If you get coding efficiency over runtime, you get a slope, and then you sort it by steepness of the slope. What you want to have is really steep. So you want to have high coding efficiency, but less runtime increase. And then for each coding tools, we developed several speed up options, so different trade-offs, and we all included these. And according to the slope, we then enabled tools successively according to increasing slope. And then you develop this Pareto set here, this curve, this light green curve. And then you just need to define a good operating points or presets that lie on that curve. So both coding tools and speed ups for coding tools. So selection of a tool and the tool set and different speed up options of a tool are influenced in this Pareto set. So there's a lot of publications, a lot of papers that we published around that. If you're interested and want to dive deeper, you can you have here the list of papers and the links to the papers. Whenever possible, we try to make them open access. So whenever it was possible, it should be open access. Otherwise, you can get it through IEEE. And this is, it will also make the slides available, so you have it offline and can, if you want to look into that, you can dive into the details with these publications related to fast encoder options, Pareto set optimizations, fast partitioning, and everything that relates to that topic. The next topic is multi-threading. I need to correct that typo. It should be multi-threading. And this is also a very important part of the VVenC encoder because it allows you to run fast on multi-core systems. And the multi-threading has CTU, so you can process CTUs in parallel once there are no dependencies, and CTU lines in parallel, like a wavefront line approach. On top of that, CTU line, you can have frame parallel. So you have multi-level, like a hierarchical parallelization approach for multi-threading. And as well for the faster and fast presets, we have a smaller CTU size. Of course, if you have smaller CTU sizes, you have more CTU lines, which also is a better scaling when using multiple threads. You can even get better multi-threading efficiency or better multi-threading scaling if you enable normative wavefront or entropy coding synchronization, where you cap the above right dependency for CTUs. You can partition your picture in tiles and process tiles independently. For low bit rates, if you would not apply loop filter over tiles, you would see tile boundaries, especially at low bit rates. So we always enable filtering across tile boundaries. So visually, you don't have an impact on that. Also, disabling it would not benefit a parallelization approach. So what is not ready there, or what is a bit the limitation of that multi-threading approach in VVenC, that you cannot scale it with a large number of threads. Like if you scale above 32 threads, you go into saturation. You do not get more speed by adding more threads, even you have like 100 cores available. So this is live encoding, and that is really not possible. So this is the limitation of VVenC. You can read all the details in this paper on ISM, efficient multi-threading strategies. I also put the link here. For the scaling, I have to say that you can see here in the charts that up to 4 threads, you get almost linear scaling. So you get a speed up of 4 up to 4 threads. And then the more threads you spend, you get less efficient for the number of threads. The speed up is not linear anymore. But you can see here that this is the fast and the medium preset, that the faster presets scale better with higher number of threads. This is, for example, due to the lower CTU size, which makes CTU parallel processing easier with more threads. So this is why you have it here. If you add wavefront parallel processing in a normative way, and for example 2x2 tiles configuration, then you can even improve the scaling for the medium and the presets. You can see here, the curves are getting closer to the ideal link. So this is how you can achieve scaling. Of course, this comes with a decrease of coding efficiency. This is always the trade-off you have here. Then there is rate control and subjective optimization. For subjective optimization, this works with some kind of a quantization parameter, QP adaptation, which is based on a modified PSNR measure. PSNR is just mean square error, and this extended PSNR or XPSNR is basically a perceptually weighted MSE metric, which makes it very easy to be integrated into rate distortion optimization decision loops in an encoder. For example, if you take VMAF as a subjective metric, it has to be computed. It's getting faster, the computation, but you have to compute it for the image. And then you can re-encode chunks of images. But if you want to do it blockwise, you cannot compute it blockwise. So that's the benefit of that extended PSNR. You can use it like the PSNR-based RDO, but this is perceptually weighted, also taking the temporal consistency and visual activity into account. This then adapts the quantization according to areas, gives a finer quantization to areas where we are more sensitive to quantization noise, and coarser quantization to areas where we are not that sensitive to quantization noise. We contributed that measurement to VVenC. You can find it also here on our GitHub, and the patches have been submitted to VVenC as well to have it as a filter, distortion measurement filter in VVenC. So if you're interested in playing with that, you can find it here. There are 3 related publications that I listed here if you want to dive more into details. Then a very interesting project we had also again for encoding presets is the low decoding energy, or a preset called low decoding energy preset. You can also consider it fast decode. This is a cooperation with the University of Erlangen-Nuremberg. And what we did there is we analyzed all the VVC encoding tools, and some of them are having a higher impact of decoding runtime, which directly relates to decoder energy consumption, than others. So what we did there in this preset, we removed some of the very high decoding energy tools from the medium preset, which was our basis. And that loss you get encoding efficiency from removing that, of course, you get faster and less energy at the decoder, but you also have a coding efficiency drop. And we compensated that by having a more increased, or allow a deeper partitioning, which is on the decoder, not increasing the complexity, but increases the encoder complexity. And we do more search on the encoder, which does not impact the decoder complexity, but impacts the encoder runtime. So overall, with this preset, we achieve a 30%, and in some cases even higher, reduction of the decoding energy, which is somehow equivalent to the decoder runtime. And we pay for that with a 50% more encoder runtime. However, we still keep our coding efficiency compared to the medium preset. So this is the thing you have to consider. If you just encode a video once, so you encode a movie once, you can spend that 50% more. If you consider that all the decodings, all the playbacks that are done for that video save energy again. So this is yet one of these trade-offs again. And we published that with Matthias Krenzler from Erlangen University in this ICIP paper from last year. The VVdeC, in short, fully compliant with main 10 profile, so 420 color format. It supports multi-platforms, Windows, Linux with different architectures, Intel, ARM, even RISC. It compiles on there. macOS supports both Intel and new ARM architectures, and Android. One of the key, I would say, technologies in VVdeC is the unified thread pool that was there from version 1. And it can utilize really a high number of threads and is independent of bitstream features. So sometimes you have to draft your bitstreams to enable WPP or some. That's what I talked, or tiles, what I talked about the encoder. So in order to allow a higher parallel efficiency for the decoder, but this threading in VVdeC is like independent of all these tools. This thread concept can also be found in other decoders. There's more recent a decoder, VVC decoder developed inside VVenC that activity started, another open VVC decoder, and this is also using a very similar concept to this. So this has proven to be very effective. Last but not least, I spent maybe 5 more minutes on applications, and one is integration in open source frameworks. What I talked about, VVenC and VVdeC, these are only the core encoder decoder libraries. So it takes YUV video, the encoder, and outputs a bitstream, and the decoder takes a bitstream and outputs YUV video. But you need, for example, something that converts an H.264 video into YUV in order to encode it. You need to encapsulate the bit stream into file format, transport stream, dash segments, and all that thing is done by a framework. On the decoder side as well, you need to unpack the container, demultiplex it, playback, and all that is done by a framework that integrates these VVenC and VVdeC libraries. So my colleague Adam had a presentation at the FOSDEM meeting in Brussels, which was well received, to make open source community a bit more aware of that. You can see the talk, the slides and everything on that web page. You can, if you're interested, you can look at that. There was a company called Spin Digital, which are doing HEVC and VVC live encoders. They submitted patches to FFmpeg to integrate VVenC and VVdeC. Yeah, we also looked at them, reviewed them. And so this integration based on these patches is ongoing. But in order to give people hints of how to use it already with the submitted patches, we set up a page on our VVenC wiki, which you can find here. That is a simple how-to and scripts how to build FFmpeg, applying these patches, build FFmpeg so you have an FFmpeg version with VVenC encoder and VVdeC decoder that fully supports dash, MP4, transport stream, and all that, and transcoding. So everything that you would expect from something integrated in FFmpeg. Quite a time ago, we published a paper together with Artem and Jean Lefebvre from GPEG, where we also showed how integration into GPEG works in order to do MP4 packaging, dash, and transport stream. This is, you can find in this open source, open access paper, which is referenced here. Then we worked a bit together with Bitmoving, cloud encoding infrastructure, a company, and they incorporated VVenC encoder in their cloud-based encoding framework and VVdeC for playback to show and to demonstrate what has been encoded in a browser playback, and also integrated in a mobile player app. There we did a webinar together explaining a bit what VVC is. You can find it on this link. And on the Mile High video conference last year, we had a talk with them how the encoding with VVenC in the cloud and playing back in a browser works. So with VVdeC, we also have a WebAssembly implementation that you can use to put a VVC web player on your web page using WebAssembly compilation. You can find the paper here under that link, and in this YouTube video, you can see the whole presentation, also with a demo of the playback and so on. And the next thing we are currently looking at is OpenGOP multi-resolution streaming. So OpenGOP is if you have the random access, and at a random access point where you want to tune in, typically you break all the dependencies, so you can tune in and you don't have dependencies. Then, since HEVC, you have the possibility to use OpenGOP, so you have pictures that reference past pictures, and if you tune in, you discard these pictures and start newly. But if you don't tune in and look at it like in a row, then you can use the efficiency of that referencing. However, if you have multi-resolution streaming and you switch from one resolution to another, you cannot reference pictures that have a different size. And then VVC has something called reference picture resampling that resamples the pictures so you can use them. So this enables OpenGOP usage for higher efficiency, even in multi-resolution streaming with Dash. You have to follow some constraints, and this is something we called constrained RESL encoding. Your high-level syntax nerds among you might know what this is, but for the others, this is something some restrictions at the encoder to restrict certain tools that would cause the drift that you have when combining two different resolution streams that has been encoded differently, to reduce the encoder drift, that you don't get visual artifacts but still have the benefits of saving. And this is analyzed very well in this paper by my colleague Robert Stupin in this PCS 21 paper. So last use case is a showcase that we did with a German broadcaster. It has a famous crime movie series every Sunday called Tatort, which is the German word for crime scene. You can see here on the picture someone pointing a gun. So this is typically crime scene movie or crime movie. And they have some video on demand service. Currently, they are using H.264, and they have this movie is then encoded with H.264 currently, or AVC with 4 megabits full HD, and then we encoded it with VVenC with 75% less bitrate, having it at 1 megabits and played back at the tablet, as you can see here side by side. VVC 1 megabit, AVC 4 megabit. It looks the same, good quality, but you save 75% just skipping going to next generation of codecs. And then the Fraunhofer ES, which is our audio, Fraunhofer Audio Institute, then used MPEG H audio, so enhanced audio with that. And we put that all into one demo, which works nicely. 5 hours on a tablet. So we have 5 hours playback, because we use the low decoding energy preset of VVenC. So that enables 5 hours playback. So the battery is not drained very fast. And this is pure software decoding. Of course, at some point, hopefully there will be hardware encoders in these devices, but until then, you're fine with full HD playback in software, at least up to 5 hours on a Samsung tablet that we used here. So this was a short overview of what is inside the open and optimized VVC implementations, VVenC and VVdeC, and what is currently going on and how they applied in real applications and multimedia frameworks. Some links here for further information, link to the final standard if you're into spec reading, and a very handy video on a workshop that we gave on a PCS with very lots of details on the techniques in VVenC and VVdeC, especially on subjective optimization, rate control, Pareto set optimization, all these topics that I just highlighted in this short, more compared to that workshop short talk. And there's also detailed VVC tutorial. So if you're into the VVC algorithm tools, how they work, a lot of tools inside VVC, a lot of things. All this is explained in detail with that I hold with Matthias Wien at ICME 2020. So that was it. Thank you very much.